So, on behalf of ISEC, I welcome all of you to this webinar and thanking Dr. Subroto Haldar for giving the excellent talk on space research. About Subroto Haldar, our secretary will say something about his CV. Shantanu?
Yes.
Please.
Yeah. So, good evening to you all. I, Professor Shantanu, the Secretary, Institute of Science, Education and Culture, commonly known as ISEC, welcome to one and all for joining in today's webinar, which is the first of its kind organized by ISEC. Today's date is a typical one, which is 10/10/2020, and on this date, we are going to start the webinar on space-based remote sensing for digital art, to be delivered by engineer Subroto Haldar as a part of the celebration of World Space Week 2020 that is being celebrated during 4th to 10th October 2020 worldwide. Our President, Professor Anil Kumar Ghosh, could not be present on today. In place of him, we have Dr. Sapna Mukherjee, Vice President, with us, and I request her to first deliver the welcome address today. Dr. Mukherjee, please. Then we introduce Dr. Subroto Haldar, Engineer Subroto Haldar, and we will start presentation. So, Dr. Mukherjee, please.
I welcome all of you in this webinar presented by Dr. Subroto Haldar on space-based remote sensing from digital art. During this day of space research, this is a very contributory talk, I hope, and we will enjoy it. And without losing further time for this standard conversation, let us get down to the seminar. Okay, thanks.
Thanks to Dr. Mukherjee for a very short welcome address. Now I will just introduce Engineer Subroto Haldar to all the persons attending this webinar. Engineer Subroto Haldar is at present Executive Council member of ISEC, that is Institute of Science, Education and Culture, and he is serving as an Executive Engineer, AI, Water Resources Investigation and Development Department, Government of West Bengal. After acquiring B preliminary from NIT Durgapur, then MCE from Jadavpur University in Geotechnical Engineering and MTech in Hydrology from IIT Roorkee, Subroto Haldar has been working as an Executive Engineer, Imagery Irrigation in State Water Investigation Directorate, that is SWID, under Department of Water Resources Investigation and Development, Government of West Bengal. Haldar started his career as an Assistant Engineer Irrigation at Surface Water Investigation Division number 4, Jalpaiguri, under SWID of GWRIND, Government of West Bengal in 1997. He has professional experiences more than 23 years in the field of hydrology, water resources engineering, irrigation, and geospatial technology applications onto this field. He has provided commendable services towards water resources investigation, planning and management in the state of West Bengal as a nodal officer of National Hydrology Project, West Bengal Groundwater. He is a visiting professional at Administrative Training Institute, Kolkata. At present, he is performing as the chairman of Indian Society of Remote Sensing, Kolkata chapter. Also, he is Life Fellow member of various professional bodies like SAEA, IWRS, IAH, IAHS, ISCA, ISH, IAHUK, ISRS, ISEC, and ISDA. He has been honored with a number of prestigious national awards like Bharat Gaurav Award and Best Citizens of India Award in 2016, Bharat Ratna Dr. APJ Abdul Kalam Excellence Award and Rashtriya Gaurav Award in 2017, Dr. Sarvapalli Radhakrishnan Lifetime Achievement Award in 2020, and all these awards areas bestowed on him as a great achiever on Indian origin in recognition for its meritorious achievements, outstanding performance, and individual academic excellence in the field of hydrology and irrigation, enhancing the image of India. Now, with this short presentation, I now request Engineer Sumant Haldar to please take the dais and start his presentation. Engineer Haldar, please. Please unmute, Mr. Haldar, please unmute and then present.
Hello.
I will request all the audiences to please mute their microphone, please. Mr. Haldar, please.
Hello. Hello, am I audible to all?
Yes, please. Please continue. Please present your screen.
Is it visible?
Yeah, please continue.
Okay. Very good evening to all members of ISEC, Kolkata. Today we are celebrating the World Space Week 2020, which have been already started on 4th October. Now we are at the end of this week. So today I will deliver a lecture on a space-based remote sensing on digital Earth. World Space Week actually started in 4th October and it will end on 10th October. So in this year, in 2020, it is decided to satellites and their broad benefits under the scheme Satellite Improves Life. This is the main slogan of the World Space Week 2020. Remote sensing satellite is the technique acquiring of information from a distance. Remote sensing satellites observe the Earth and other planetary bodies using remote sensor mounted on satellites that direct and record reflected or emitted energy. Remote sensors provide a global perspective and wealth of data about Earth system, enabled to form a digital Earth, which helps us to do data-informed decision making based on the current and future state of our planet. Sputnik is the first satellite launched in the space by NASA on 4th October 1957 and thus begins the space of age. That's why the remote sensing, that's why the Space Week is celebrated on the 4th October and it will end at 10th October. Satellites for observing the Earth's surface have been used since the 70s. The first land cover satellite named Landsat-1 was launched by the United States of America on July 23rd in 1972. Aryabhatta is the first Indian satellite launched in the space by Russia on April 19 on 1975. ISRO launched the first Indian satellite in the space, that is Bhaskara-1, on 7th June in 1979. According to the United Nations Office of Outer Space Affairs, almost 600 Earth observation satellites are currently in the orbit of our planet, operated by various countries and fulfilling different tasks. ISRO has started its journey in 1979 on 7th June by launching Bhaskara-1 in the space and continuing this journey and in the December 11, 2019 by the Reset-1 2BR1. Now total 38 number of satellites has been launched by ISRO till now. Satellites resides in three primary type of orbits. One is polar, second one is non-polar low Earth orbit, and third one is geostationary. Polar orbiting satellites. These are in an orbital plane that is inclined at nearly 90 degrees to the equatorial plane. This inclination allows the satellite to sense the entire globe, including the polar origin, providing observations of locations that are difficult to reach via ground Earth. Many polar orbiting satellites are considered sun-synchronous, which passes, Many polar orbiting satellites are considered as sun-synchronous, which passes over the same location at the same solar time each cycle. Satellites in ascending orbit are moving south to north when their path crosses the equator. Satellites in descending orbits are moving north to south. Polar orbiting satellite provides daily coverage of the globe. Example is the NASA Joint Polar Satellite System, that is JPSS. Non-polar low Earth orbits are at an altitude are typically less than 2,000 km above the Earth's surface, which do not provide the global coverage but instead cover only the partial range of latitude. A non-polar low Earth orbit satellite covering from 65 degrees north to 65 degrees south. Global Precipitation Mission Satellite and International Space Station are the non-polar low Earth orbit satellite. Geostationary satellite. Geostationary satellites appears to an observer on the Earth to be fixed in one location, as this satellite follows the Earth's rotation and travel at the same rate of rotation, capturing the same view of Earth with each observation and thus provide almost continuous coverage of an area. Geostationary Operational Environmental Satellite, that is GOES satellite, is one of the examples of the geostationary satellite. This orbital radius of the satellite from the center of the Earth, it is calculated by this formula G into m into t square divided by 4 pi square whole to the power 1/3. And if we put the Newton's constant gravity and mass of the Earth and orbital period, then we can calculate the orbital radius of the geostationary satellite, that is 35,790 km. Satellite observation with electromagnetic spectrum. Electromagnetic energy produced by the vibration of charged particles travels in the form of waves through the atmosphere and the vacuum of space. These waves have different wavelengths and frequencies. A shorter wavelength has a higher frequency. Some like radio, microwave and infrared waves have a longer wavelength, while others such as ultraviolet, X-ray and gamma rays have a much shorter wavelength. Visible light sits in the middle of that range of long to short wave radiation. This is a small portion of the energy is all the human eye able to detect. Instrumentation is needed to detect all these forms of electromagnetic energy. Remote sensing satellite bond sensors utilize this full range of the spectrum to explore and understand the processes occurring in the Earth. Satellite observing with electromagnetic spectrum. Weather and communication satellites take the advantage of waves absorbed or reflected by elements in the atmosphere like water, vapor, and carbon dioxide. Some wavelengths allow for unimpeded movement through the atmosphere. Visible light has wavelengths that can transmit it through the atmosphere. Microwave energy has wavelengths that can pass through clouds. The primary source of energy observed by satellite is the sun. The amount of the sun's energy reflected depends on the roughness of the surface and its albedo, which is how well a surface reflects light instead of absorbing it. Snow has a very high albedo, reflecting up to 90% of the energy it receives from the sun, whereas the ocean reflects only about 6%, absorbing the rest. The energy absorbed by the ocean gets re-emitted at longer wavelengths as infrared radiation. All things of the Earth reflect, absorb, and transmit energy, the amount of which varies with the wavelength. Spectral signature. Here we see the spectral signatures, that is this red line, it is the snow and ice, this blue line, it shows the clouds, and this yellow line, it is the vegetation, and this brown, light brown, this is dry soil, and this deep brown is wet soil, and this blue line is turbid water, and light blue is clear water. Active and passive sensors. Sensors on board satellite use the sun as a source of illumination or provide their own source of illumination, measuring the energy that is reflected back. Passive sensors use natural energy from the sun. Active sensors provide their own source of energy. Active sensors include different types of radio detection and ranging, that is radar, sensors, altimeter, and scatterometers. The majority of the active sensors operate in the microwave band of the electromagnetic spectrum, which gives sensor the ability to penetrate the atmosphere under most conditions. Active sensors are useful for measuring the vertical profile of the aerosols, forest structure, precipitation and wind, sea surface topology, and ice. Passive sensors include different types of radiometers that quantitatively measure the intensity of electromagnetic radiation in selected bands, and spectrometers that are designed to detect, measure, and analyze the spectral content of reflected electromagnetic radiation. Most passive sensors used by the remote sensing applications operate in the visible infrared, thermal infrared, and microwave portion of the electromagnetic spectrum. Passive sensor measures land and sea surface temperature, vegetation properties, cloud and aerosol properties, and other physical properties. The satellite resolution plays an important role in how data from a sensor can be used. Resolutions varies with the satellite's orbit and sensor design. 4 types of resolution is considered for any data set collected from the satellite. That is, one is radiometric, another one is spatial, another one is spectral and temporal. Radiometric resolution is the amount of infrared in each pixel, that is number of bits representing the energy recorded. Each bit record an exponent of power 2, and 8-bit resolution is 2 to the power 8, which indicates that the sensor has 256 potential digital values to store information, that is 0 to 255. The higher the radiometric resolution, the more values are available to store information, providing better discrimination between even the slightest difference in the energy. While assessing water quality, radiometric resolution is necessary to distinguish between suitable differences in the ocean color. Here there is 3 resolutions, radiometric resolution are shown. This is 2-bit resolution, this is 4-bit resolution, and this is 8-bit resolution. Spatial resolution. It is defined by the size of each pixel within a digital image and the area on the Earth's surface represented by the pixel. Moderate resolution imaging spectral radiometer, that is MODIS satellite. Its spatial resolution is 1 kilometer. Pixel area represents 1 kilometer by 1 kilometer area on the ground. Bands with a spatial resolution is 250 meter or 500 meter. The finer resolution, the finer the resolution, the lower is the number. Here, the 30 meter pixel image, and this is 100 meter pixel image, and this is 300 meter pixel image are shown. Spectral resolution. It is the ability of a sensor to discern finer wavelengths, having more and narrower bands. Many sensors are considered to be multispectral, having between 3 to 10 bands. Sensors that have 100 to even 1000 of bands are considered as to be hyperspectral. The narrower the range of wavelengths for a given band, the finer the spectral resolution. Airborne visible or infrared imaging spectrophotometer, that is IRIS, captures information in 224 spectral channels. At this level, detailed distinction can be made between the rock and mineral types, vegetation type, and other features. Temporal resolution. It is the time it takes for a satellite to complete an orbit and revisit the same observation area. This resolution depends on the orbit, the sensor's characteristic, and the south wind. Geostationary satellites match the rate at which the Earth is rotating. The temporal resolution is much finer at about 30 seconds to 1 minute. Polar orbiting satellites have a temporal resolution that can vary from 1 day to 16 days. MODIS satellite has a temporal resolution of 1 to 2 days, allowing us to visualize the Earth as it changes day by day. Landsat has a narrower south width and a temporal resolution of 16 days, showing not daily changes but bi-monthly changes. Geometric resolution. It refers to the satellite sensor ability to effectively image a portion of the Earth's surface in a single pixel and is typically expressed in terms of ground sample distance, that is called GSD. GSD of Landsat is 30 meter, which means the smallest unit that maps to a single pixel within a range of image is 30 meter by 30 meter. GSD of latest commercial satellite, that is GOI-1, is 0.41 meter resolution. GSD of military film-based reconnaissance satellite, that is Corona, the resolution is 0.3 meter. Creating satellite imagery. Many sensors acquire data at different spectral wavelengths. Landsat 8 band 1 acquires data 0.433 to 0.453 micrometers. MODIS band 1 acquires at 0.62 to 0.67 micrometers. Bands can be combined to produce imagery of the data to reveal different features in the landscape. Landsat 8 has a total 11 bands, whereas MODIS has 36 bands, all measuring different regions of electromagnetic spectrum. For a true color, that is red, blue, green, image from Landsat bands 432 are combined respectively. Image interpretation. Satellites for image interpretation. First, we have to know the scale. There are different scales based on the spatial resolution of image, and each scale provides different feature of importance. Next, look for the pattern, shapes, and the texture of the image. Many features are easy to identify based on their pattern or shape. Agricultural areas are very geometric in shape, usually circles or rectangles. Straight lines are typically man-made structures like roads or canals. Define colors. When using color to distinguish features, it's important to know the band combination used in creating the image. True or natural color images are basically what we see with our own eyes if looking down from the space. Water absorbs light, so typically it appears black and blue. However, Sunlight reflecting off the surface make it appears gray or silver. Sediment can affect water color, making it appears more brown, as can algae, making it appears more green. Vegetation ranges in color depending on the season. In the spring and summer, it's typically a vivid green. Fall may have orange, yellow, and tan, and winter may have more browns. Bare ground is usually more shade of brown. Urban areas are typically gray from the extensive concrete. Ice and snow are white. Quantitative analysis. Different land cover types can be discriminated more readily by using image classification algorithm. Image classification uses the spectral information of each individual pixel. A program using image classification algorithms can automatically group the pixels in what is called unsupervised classification. The user can also indicate areas, known land cover type, to train the program to group those like pixels. This is called supervised classification. Map or imagery can also be integrated into geographical information system, that is GIS, and then each pixel can be compared with other GIS data such as census data. Satellites also often carry a variety of sensors measuring biogeophysical parameters such as sea surface temperature, nitrogen dioxide, or other atmospheric pollutants, winds, aerosols, and biomass. These parameters can be evaluated through statistical and spectral analysis technique. Satellites remote sensing technique. What is a remote sensing technique? Remote sensing is a science of obtaining information about an object, area, or phenomena through the analysis of data acquired by a device that is not in direct contact with the object, area, or phenomena under investigation. In a more restricted sense, remote sensing usually refers to the technology of acquiring information about the Earth's surface, that is land and ocean, and atmosphere using sensor on board airborne, aircraft or balloon, or spaceborne, that is satellite or space shuttle platform. Information carrier in remote sensing. In remote sensing, the sensors are not direct contact with the object or event being observed. The information needs a physical carrier to travel from the object or event to the sensors through an intervening medium. The electromagnetic radiation is normally used as an information carrier in case of remote sensing technique. The output of remote sensing system is usually an image representing the scene being observed. A further step of image analysis and interpretation is required in order to extract useful information from the image. The human visual system is an example of a remote sensing system in this general sense. Component of remote sensing system. There are two types of component broadly classified. That is, one is data acquisition system. It consists of energy source, propagation of energy through the atmosphere, energy interaction with the Earth's features, airborne or spaceborne sensors, generation of census data in pictorial or numerical form. And another is the data analysis process. It consists of examining the data using various viewing and interpretation devices, data presentation in the form of maps, tables, or reports, and data usage in decision-making process. Energy sources and radiation principles. Sun is the most obvious source of electromagnetic radiation for remote sensing technique. All objects are bathed in electromagnetic energy or radiation covering a broad continuum of wavelength. Visible light is the only one of many forms of electromagnetic energy. Radio waves, heat, ultraviolet rays, and X-rays are other familiar forms. The characteristic of electromagnetic radiation given by particle theory explains that how this energy interacts with the matter. This theory suggests that electromagnetic radiations are composed of many discrete units called photons or quanta. Here the electromagnetic spectrum is shown, that is gamma rays, X-rays, ultraviolet rays, infrared rays, radar, FM, TV, shortwave, and AM. Electromagnetic wave. Energy of quantum can be calculated by this formula E is equal to HF. E is the energy of quantum, H is the Planck constant, and F frequency. Electromagnetic waves is characterized by the general equation C is equal to F lambda. C is the velocity of light, F is wave frequency, and lambda is the wavelength. And combining these two equations, we can get E is equal to Hc by lambda. That is energy of a quantum of inversely proportional to its wavelength. The longer the wavelength involved, the lower its energy content. And ultimately, the amount of energy that an object radiates is among the things in function the surface temperature of the object. This property is expressed by the Stefan-Boltzmann law, which states that W is equal to into T to the power 4. So T is the absolute temperature and Stefan-Boltzmann constant is sigma. The total energy emitted from an object varies with T to the power 4. That is, increases very rapidly with increase in temperature. Maximum spectral radiant emitters from the Earth's feature occurs at a wavelength of about 9.7 micrometer. This corresponds to thermal infrared energy, which can neither be seen nor photographed, but can be sensed with such thermal devices as radiometers and scanners. Energy interactions in the atmosphere. Atmosphere is not completely transparent. The outgoing spectral radiance of object at the Earth's surface is modified before it reaches the sensor. The atmospheric gases, carbon dioxide, ozone, water vapor causes reflection, scattering, and attenuation of energy, so that only a few windows are available through which part of all the pertinent radiation is transmitted. On atmospheric window exists in the visible spectral region, that is 0.4 to 0.7 micrometer. There are three windows in the infrared region, that is 3 to 4.5 micrometer, 8.5 to 14 micrometer, and 17 to 19 micrometer. This atmospheric transmission system is electromagnetic spectrum is shown here. Energy interaction with Earth surface features. When electromagnetic energy is incident on any given Earth surface feature, then various fractions of energy incident on the elements are reflected, absorbed, and or transmitted. The reflectance characteristic of the Earth surface features may be quantified by measuring the portion of the incident energy that is reflected. This is measured as a function of wavelength, and it is called spectral reflectance, that is R. It is mathematically defined with this formula. That is energy of that. It is one of the ratio, that is energy of wavelength reflected from the reflected from the object divided by energy of the wavelength incident on the object into 100. Spectral reflectance of soil. The majority of radiation incident on soil surface is either reflected or absorbed, and little is transmitted. The characteristic of soil that determines its reflectance properties are its soil moisture content, organic matter content, texture, structure, and iron oxide content. The soil curve shows less peak and valley variations. The presence of moisture in soil decreases with its reflectance. Spectral reflectance of vegetation. The spectral characteristic of vegetation vary with wavelength. Plant pigmented leaves called chlorophyll strongly absorb the radiation in the red and blue wavelength but reflects green wavelength. The internal structure of the healthy leaves act as a diffuse reflector of near infrared wavelength. Measuring and monitoring the near infrared reflectance is one way that scientists determine how healthy particular vegetation may be. Spectral reflectance of water. In case of water, majority of radiation incident upon water is not reflected but is either absorbed or transmitted. Longer visible wavelengths and near infrared radiation is absorbed more by water than by the visible wavelengths. Thus, water looks blue or blue-green due to stronger reflectance at these shorter wavelengths and darker if viewed at red or near infrared wavelengths. The factors that affect the variability of reflectance of a water body are depth of water, materials within the water, and surface roughness of the water. Platforms for remote sensing. Platform of remote sensing can be fixed or moving, operate from low or orbital altitudes, and be either manned or unmanned. They may be temporary, semi-permanent, or virtually permanent. The elevation of altitude of platform has direct effect on the scale of the data and the size of the area that is imaged. Remote sensing sensors is an instrument which measures electromagnetic radiation from the object within the specific electromagnetic spectrum. Field of view of sensor provides appropriate coverage from the aerial or orbital platform. Sensors most widely used are cameras with quartz lens for use with ultraviolet flame. Spectral scanners, optical, mechanical scanners, radiometers. This can be active microwave sensors such as side-looking airborne radar, that is SAR, and synthetic aperture radar, that is SAR, or passive sensors. Here some Indian satellites are shown here. 1988 IRS-1A, and then in 1994 IRS-P2, IRS-1C 1995, IRS-1D 1997, and Cartosat 2007. The span stereo is 1 meter resolution and 12 kilometers short. It is the latest achievement in case of resolution of the from the Indian satellite. That is 1 meter resolution. Data acquisition and interpretation. Earth viewing sensors will normally generate a voltage or frequency signal corresponding to the measurement being made. The analog signal is converted into the digital signal. for transmission to the Earth on the binary coding. Such radiant is generally expressed in the gray level range from 0 to 255, which records 8 bits for every pixel value. Detection of electromagnetic energy can be performed either by photographic or electronic means. The electronic sensors generate electrical signals that are generally recorded onto the magnetic tape. Thus, the data interpretation aspect of remote sensing involves analysis of pictorial or numerical data. The data obtained from the remote sensor are kept in BSQ or BIL or BIT format. The digital receipts from the sensors are stored in one of these formats, that is band sequential BSQ, band interleaved by line, that is BIL, and band interleaved by pixel, that is BIP. Reference data. Reference data about the resources being studied, such as soil map, topographical sheets, or field check data, etc., are used to assist in the data analysis. With the aid of reference data, the analysts extract information about the type, extent, location, and condition of various resources over which the sensor data were collected. Rarely, remote sensing is employed without the use of some form of reference data. This is panchromatic image. It consists of only one band. It is usually displayed as a grayscale image. That is, the displayed brightness of a particular pixel is proportional to the pixel digital number, which is related to the intensity of solar radiation reflected by the target in the pixel and detected by the detector. Thus, a panchromatic image may be similarly interpreted as a black and white aerial photograph of the area. The radiometric information is the main information type utilized in the interpretation. Color composite image. In displaying a color composite image, 3 primary colors, that is red, blue, and green, are used. When these 3 colors are combined in various proportions, they produce different colors in the visible spectrum. Associating each spectral band, not necessarily a visible band, to a separate primary color result in color composite image. True color composite image. If a multispectral image consists of 3 visual primary color bands, red, green, and blue, the 3 bands may be combined to produce a true color image. The band 3, that is red band, and 2 green band and 1 blue band of a Landsat TM image or Iconos multispectral image can be assigned respectively to red, green, and blue colors for display. The colors of resulting color composite image resembles closely what would be observed by the human eye. First, color composite. This display color assignment of any band of a multispectral image can be done in an entirely arbitrary manner. In this case, the color of a target in the displayed image does not have any resemblance to its actual color. That's why it is called first color composite image. A very common FCC scheme for displaying the satellite for the observation dealer terrain, that is a spot. Here the FCC multispectral spot image is displaced and multispectral image is shown below, that is near infrared and red band and green band. In FCC image, vegetation appears in different shades of red depending on the types and condition of the vegetation, since it has a high reflectance in the NIR. Clear water appears dark bluish, higher green band reflectance, while turbid water appears cyan, higher red reflectance due to sediments compared to clear water here. Bare soil roads, buildings may appear in myriad shades of blue, yellow, or gray depending on their composition. Natural color composite. For optical image lacking of one or more of 3 visual primary color bands, that is red, green, blue, the spectral bands may be combined in such a way that the appearance of the displayed image resembles a visible color photograph. That is, vegetation in green, water is blue, soil is brown, and this composite is referred to as true color or natural color composite. Here the spot HRV multispectral sensor does not have a blue band. These 3 bands, XS1X, XS2, and XS3 correspond to green, red, and NIR band respectively. This is from the NCC multispectral spot image. Now I am covering some applications of remote sensing for digital Earth. Textural information. Texture is an important aid in visual image interpretation, especially for high spatial resolution imagery. An example is shown below. It is also possible to characterize the textural features numerically, and algorithms for computer-aided automatic discrimination of different texture in an image are visible. Vegetation indices. Different bands of multispectral image may be combined to accumulate the vegetative areas. Ratio vegetation index, that is RVI, is equal to near infrared divided by red. Since vegetation has high NIR reflectance but low red reflectance, vegetative area will have higher RVI values compared to non-vegetative areas. Normalized difference vegetation index, that is NDVI, it is the ratio of difference between NIR minus rate and NIR plus rate. That is reflectance in NIR wavelength, rate is reflectance is red wavelength. In NDVI map, the bright areas are vegetated while the non-vegetated areas like buildings, clearings, river, sea are generally dark. The trees lining on the road are clearly visible as grey linear features against the dark background. NDVI band may also be combined with other band of multistructural image to form a color composite image which helps in to discriminate different types of vegetation. So this NDVI indices is very useful to detect the vegetative cover. Another one is soil adjusted vegetation index. In cropped area, the soil background may be reflected that influence the satellite observed in reflectance, which ultimately influences the NDVI value. The HUT presents the concept of soil adjusted vegetation index to avoid soil reflectance with this formula. He reported that soil background influence on the crop canopy reflectors were adequately minimized for canopy over ranging from the sparse to dense with value of L and adjustment factor that is 0.5. Soil water monitoring. These crop coefficients are used for soil water monitoring, and from this crop coefficient, crop evapotranspiration is calculated. And from this crop evapotranspiration, monthly irrigation water demand and now is calculated. And from monthly water demand, irrigation scheduling and planning for water resource development can be done. So satellite data is very useful for irrigation. Soil moisture monitoring. Soil moisture is a very important variable in hydrology because its variance influences the evolution of weather and climate. Soil moisture controls the runoff, affects the vegetation growth, and plays a significant role on evaporation and transpiration at the land surface boundary as well as surface energy. Active and passive remote sensing system, and especially those operating in the microwave region of the electromagnetic spectrum, have shown the ability to measure the soil moisture content since it is very sensitive to the dielectric properties of the soil. Low frequency microwave has the advantage of longer penetration, therefore less atmospheric effect. Soil moisture and ocean salinity SOMS mission has been designed to observe the soil moisture over the globe land with the first ever polar orbiting space-bound radiometer. This novel technique of SOMS mission will provide operational monitoring of water in soil. Snow cover monitoring. Snow cover data extracted by the satellite remote sensing is immediately usable in snowmelt runoff model for both simulation and forecasting of the snowmelt runoff. Moderate resolution image spectral radiometers, that is MODIS, satellite by NASA, provide weekly global snow cover information. Snow cover products derived from the MODIS are based on the band rationing of MODIS band 4 and band 6. These bands are used to calculate the normalized difference snow index. Water storage monitoring. Changes in terrestrial surface water storage affect the gravity field, where the added water must extract a slight additional attraction. Precise measurement of changes in the gravity field sensed by the orbiting satellite give information about the seasonal and interannual shifts in the surface mass distribution. Overland, the filling and emptying the water pool, including soil and aquifers, is the main contributor to the gravity change. Though hydrologically irrelevant contributions such as glacial rebound of the lithosphere exist and must be subtracted from the total gravity signal to estimate the change in water storage. Gravity Recovery and Climate Experiment, that is GRACE satellite, is a pair of NASA satellite launched in March 2002 that measures Earth's gravity field from the orbits of about 500 km height. Small change in distances between the satellite due to gravity field variation is measured via onboard K-band microwave signal and the Global Positioning System, that is GPS. GRACE generates map of gravity anomalies of approximately monthly time resolution of 250 km spatial resolution. Another application is flood monitoring. Flood mapping needs real-time coverage, and unfortunately, the clouds frequently are present when the floods occur. Some excellent NIR flood mapping has been performed, but only when cloud-free images can be acquired. As a result, a prime research area is used of satellite-based radar to provide high-resolution all-weather coverage at the time of flooding. Water bodies monitoring. Because water is essentially distinguishable in the near-infrared spectral region, water bodies larger than 0.02 square kilometer can be mapped using the Landsat multispectral sensors. The availability of higher resolution Landsat TM and thematic mapper and spot data enhances this long-established capability, and mapping of smaller water bodies is possible. The presence of clouds become an additional complicating factor. Surface water inventories can wait until the clear sky images are acquired. Surface water quality monitoring. Remote sensing of monitoring water quality has been started in early 1970s, and suspended sediment are generally equated with this equation y equal to a plus bx or y equal to a into b to the power x. Y is the remote sensing measurement radius reflectance energy. X is the water quality parameter of the interest, that is suspended solid or turbidity, and A and B are empirically derived factor that this value are gained from the statistical relationship we determine from spectral reflectance value and between in situ water quality parameters. From the spectral reflectance, it can give the information about the band or wavelengths are suitable for that water quality parameters. Suspended solid monitoring in case of river water. Suspended solids are most common organic and inorganic pollutants in surface water. Suspended sediments can be mapped with remotely sensed data. Suspended sediment increases the radiance from the surface water visible and near infrared range of the electromagnetic spectrum. By in situ studies, the wavelength between 700 and 800 nanometer is the most useful range for determining the suspended matter in the surface water. Here, the Landsat thematic mapper image showing the categories of suspended solid. Turbidity monitoring. Water turbidity is an expression of the optical properties of the water, which cause the light to be scattered and absorbed rather than the transmitted in the straight lines. As water turbidity is mainly caused by the presence of suspended matter, turbidity measurement has often been used to calculate fluvial suspended sediment concentrations. The best correlation of turbidity of reflectance was red reflectance. ICONOS high-resolution satellite data has been used for mapping turbidity of the river water. Another is color dissolved organic matter monitoring, CDOM. It consists of naturally occurring water-soluble, biogenic, and heterogeneous organic substances that are yellow to brown in color. CDOM is the fraction of dissolved organic matter that absorb light in both ultraviolet and visible range. DOM also affects the volume reflectance volume spectrum, but almost exclusively at the shorter wavelengths. CDOM absorbs the visible light spatially below the 500 micrometer, and its absorbance increases exponentially with the decreasing wavelength. Absorbance of red light can be significant at the high CDOM concentration. CDOM concentration also increase in coastal water due to the in situ creation of folic acid produced from the seaweed decomposition as a byproduct of primary production stimulated by nutrients and the anthropogenic input of industrial or domestic effluents from the populated area. In coastal environment, the optical properties of the CDOM change owing to the seawater mixing and photodegradation. Chlorophyll monitoring in water bodies. Eutrophication of a water bodies can be quantified in terms of concentration of chlorophyll contained in the algal plankton. Chlorophyll is one of the photosynthetic agents contributing to the color of the water. Monitoring the concentration of chlorophyll, that is algal and phytoplankton, is necessary for managing the eutrophication in the water bodies. Remote sensing has been used to measure the chlorophyll concentration spatially and temporally. As with the suspended sediment measurement, most remote sensing studies of chlorophyll in water are based on empirical relationship between radiance or reflectance in narrow bands or band ratios and chlorophyll. Measurement from aircraft, Landsat or Spot or CYFS or CZCS has used a variety of algorithms and wavelengths to map chlorophyll of the ocean, estuaries, and the fresh water. Lineaments mapping also used for groundwater monitoring. Remote sensing data assimilation in real time could be a bulk tool for geological feature extraction and mapping. Edge automatic detection algorithms such as Laplacian, Sobel, and Canny are the major image processing tool for lineament features detection in the remotely sensed data. Landsat thematic mapper satellite image distinguish clearly the appearance of lineaments which are associated with fractures and faults. Canny algorithm first smoothens the image of eliminate the noise. It then finds the image of gradient to highlight the regions with high spatial derivatives. In hard rock areas, groundwater potential can be monitored through detection of interconnected lineaments thereof. Here, the lineament mapping is showing using the Kenny algorithm. In conclusion, we can say that remote sensing is the key technique used to obtain information related to the Earth's resources and the environment. And technology's progress in remote sensing sensors enables us to obtain data on the global scale, remarkably expanding humanity's understanding of its own living environment from a spatial and temporal perspective, and provides an increasing number of data resources for the digital Earth. Thank you. Thank you all.
Thank you, Mr. Haldar, for a nice presentation. And a lot of unknown things are presented and pointed out by Mr. Haldar. Now the session is open for any question and answer from the audience. Any question from the audience, please? Any question? I can ask one question to Mr. Haldar to know how the thing is done. Hello? Hello?
Hello?
Suppose I am having one river flowing and also there is one snow covered area, and both may be appearing as white band. How can it be distinguished? You have pointed out a bit, but can you please elaborate that?
In case of snow cover, the temporal resolution from the temperature anomalies, we can distinguish the snow cover and the flowing water.
Although the color appears to be same, but you can find out that.
Color is same, but we can distinguish from the temperature, and that can be detected by the sensor. That is temporal resolution.
And suppose it is a forest cover and there is one say paddy field, can this be distinguished clearly?
Yes, it is distinguished from its texture that I have shown in one slide. From the textural pattern, we can distinguish the forest cover and the vegetative cover, and also the NDVI indices, what I have already shown, that is NDVI indices from we can calculate, and we can distinguish the forest cover and the vegetative cover from this NDVI value.
So now is it possible to find out the mine, where is copper mine, where is iron ore, etc.? Is it possible?
Yes. It is also can be distinguished, because iron ore, that is color will be different from the soil color. It will be,
but it is
more red.
But it's underground, so this underground presence of iron or copper also can be found.
No, it is underground. No, it is, if it is open cut mine, then we can detect whether iron ore is present or not.
So
but it cannot.
We cannot. Underground one, we cannot.
No. If it is open cut mine, then it is detected. But in case of underground, it is not possible.
Okay. Any other questions for anybody? Dr. Mukherjee, can you please comment something? Dr. Sapna Mukherjee, please unmute and say a few words. Hello. Dr. Mukherjee, can you please make some comments or say a few words? Hello. Dr. Mukherjee, please unmute and say something. Dr. Mukherjee. Dr. Sapna Mukherjee. Hello. Hello. Anyway, any other question from anybody? Dr. Bornola Borman is there. He is also working in the area of pattern information, etc. Can you please put some comments? Dr. Borman?
Yes.
Yeah.
I want to know, in present scenario, it can be possible to detect some places using any remote sensing method where this pandemic is growing very rapidly.
Actually, where the pandemic is growing in rapidly, the GIS tool is using for mapping now.
Okay.
Remote sensing image is not applicable there, but number of pandemic situations we have plotted in the digital map with the use of GIS software. That
Okay.
is Geographical Information System software.
Yes. Okay. Thank you, sir.
Okay. So any other questions or any other comments? Dr. Sapna Mukherjee, can you tell something? Hello. Okay. If there is no other question or query, then I can just say a vote of thanks at the end. In fact, the Executive Council members of the Institute of Science, Education and Culture have opined to arrange this kind of webinars among this ongoing pandemic situation, where physical presence in a seminar is not possible, because nobody will hire any seminar room or something to organize this kind of seminar. So we have thought of to arrange regularly this kind of webinars, and this is the first one that engineer Subrata Haldar has come up with this idea of delivering one webinar. I personally thank engineer Subrata Haldar to agree to deliver this first webinar of its kind organized by ISEC among this ongoing pandemic situation. Also, I thank personally Dr. Sapna Mukherjee, who is the Vice President of ISEC and also convener and chairperson of the seminar committee of ISEC, so who single-handedly handles many of the seminar and webinar activities. Obviously, in case of webinars, I have to take a lot of things to do, but otherwise, many other members, etc., of the seminar committee are also taking key decisions to organize a lot of webinars. So this is the first one of its kind. Professor Amit Kumar Research could not join today, but he was the main support behind all these activities of ISEC. I also thank him personally to make all the background support. And then I acknowledge the presence of Roger Kotihar, who is the key man behind different ISEC activities. So in fact, ISEC office was closed for the last few months, and day before yesterday only, this office was opened, and ultimately the ISEC office activities could be started regularly, and lot of other pending works are being carried out by him. So he's also there today, and he's joining and overseeing all the going on in the webinar. So all the persons in the audience who are there in the Google Meet platform, and all such persons who have joined also in the YouTube platform, all are thanks for following this webinar. And the fourth lane channel, the fourth lane YouTube channel has made live streaming of this particular webinar, this first webinar arranged by the ISEC. And I also personally thank them for coming up to live telecast, live stream this particular webinar. So with these words, I hope all of you will be joining together and in the future webinars organized by the ISEC. And with these words, with the puja coming on, stay safe and enjoy puja at home or limited exposure to the puja pandals, etc. With a lot of safety precautions. I hope you will enjoy, and you will also enjoy the future webinars organized by the ISEC, Institute of Science, Education and Culture. And with this word, I make another thanks to all, and good evening to all for making a goodbye to you. Thank you all.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, everybody.
Yeah. Goodbye.
Bye.
Thank you.